Welcome to today's lesson. In this first tutorial, we will begin to graph our rational functions. So we are in section 3.4 in our textbooks, and we are going to begin graphing. There are a bunch of things that we can find to help us to graph our rational functions. So I'm stating them here in a list, so you can always refer to this list to remind yourself how to find these things. So number one, we're going to find and dash our vertical asymptotes. Remember, that is setting the denominator equal to 0. And remember, that is going to be x equals some sort of number. It's going to be an equation of a vertical line. Step 2, find and dash our horizontal asymptotes. That depends on the degrees. Remember, there are 3 cases, and that depends on our degrees. That's going to be y equals some number, a horizontal line. Step 3, possibly find and dash a slant asymptote. I put a question mark here because obviously we don't always have a slant asymptote, but if we did, we can either use our long or our synthetic division. And that's going to be an equation of a line in y equals mx plus b form. So those are our asymptotes. Step 4, not that you have to go in this order, but I'm going to try and stay consistent and go in this order. Step 4, find and plot if you have any x-intercepts. That is when you set the numerator equal to 0. Oops. Step 5, find and plot the y-intercept. Of course, there'll only be one y-intercept for a function if we have one. That is when you set x equal to 0. Basically, you're evaluating f of 0. You're plugging a 0 into your function. Once you have all of these things and you've basically created a shell of what your graph is going to fit into, at least that's what I like to call it, the shell, then I'd like you to use your calculator and graph the thing on your calculator and see where all the little parts of the curves, how they fit into your shell. Once you've done that, it's pretty easy to find your domain and your range, and I'd also like to state the end behavior. So let's look at a few examples. I've got a of x and b of x here. Let's go through our whole list. Let's first start by finding our vertical asymptote. And I'm going to try and color code each of my graphs. If you have a bunch of different colors, that might be helpful. Our vertical asymptote happens when our denominator is equal to 0 and we solve that equation. And actually, that equation is already solved for us. X equals 0. So it looks like x equals 0 will be our vertical asymptote. I'm going to dash that in. Next, let's go to our horizontal asymptote. Our horizontal asymptote depends on our degrees. The degree of the numerator and the degree of the denominator are identical, so therefore I know that I take the leading coefficient, which is 2 divided by 1. So y equals 2 will be our horizontal asymptote, and I will dash that in. Let's go to our x-intercept. I know I don't have a slant asymptote, of course, since I have a horizontal one. Let's go to the x-intercept. The x-intercept comes from the numerator being set equal to 1. I can solve this one pretty easily in my head. Add 1, divide by 2, and my x-intercept is 1/2. So I'll put that as a dot on my x-axis. And let's do our y-intercept. Our y-intercept is when x equals 0. So this term would become 0 and this term would become 0. And if you notice, for our y-intercept we would have -1 divided by 0, but obviously that is no good, so we do not have a y-intercept. And it kind of makes sense because our y-intercept was actually, our y-axis was covered up with this vertical asymptote. So this is everything that we can do by hand, and I have a pretty good sense of what my graph is going to look like, but just in case you do not, why don't you pull up your calculator, let me slide this on over, and let's graph this on the calculator and actually just confirm that this does fit into our shell. The only thing you definitely need to watch out for when you're graphing on the calculator needs to know what the entire numerator is in parentheses and what the entire denominator is in parentheses. So please make sure that you're doing that. Otherwise, you're not speaking to the calculator correctly. So I'm going to start with my parentheses and put the 2x minus 1 in the numerator. Close my parentheses, hit the division, and then I'm going to put the x in the denominator. I know when it's just a monomial, you don't really need it, but it never hurts. I'm going to press zoom 6 because I don't know, this is the first time I'm using the calculator in a while, and I just want to make sure that we're in our normal zoom. And that makes sense. I can see what my rational curve looks like, and I can see that that fits nicely into my shell. Please make sure that you are crossing any intercepts that you've already dotted. So there's my x-intercept. And then the only thing just watch out for is make sure that you're not touching the asymptotes, but also make sure that you're not curving away from the asymptote either. And you just fit your curve right into there. And that's nicely done. Let's do our domain and our range and our end behavior. So our domain, I know we could have done our domain as soon as we knew what our vertical asymptote is, because basically the vertical asymptote is going to be the one value or the two values, however many asymptotes there are, that x cannot be equal to. So since x cannot be equal to 0, that's what my domain will be. My range, in this case, my range is just a single restriction. It's just the horizontal asymptote that cannot be in the range, which is the value of 2. So I'm going to do set notation again, y such that y is not equal to 2. And my end behavior, I can describe both ends at the same time because both ends do the same thing. The far right end is approaching the value of 2. The far left end is also approaching the value of 2. And this is a of x. If we wanted to describe the middle behavior, we could do that as well. Why not practice that? As x approaches, let's see, we've got our vertical asymptote here, which is the value of 0. So we can approach 0 from the right side, and we can approach 0 from the left side. And we've got two different things that the function is doing, which is why I need to split up my two statements. When we approach 0 from the right side, you can get to the value of 0 and then get on the right side of it, and then infinitely get closer and closer and closer to 0 from the right side. You can see that this brown function is pointing all the way down to negative infinity. And on the other side of 0, on the left side of the asymptote, if we start approaching from the left side, closer and closer and closer to 0, you can see that the function this time is skyrocketing to positive infinity. So we can describe the end behavior, or we could describe the asymptotic behavior. Let's look at b of x. We'll go in the same order and the same colors. Vertical asymptote first. The vertical asymptote comes from the denominator being set equal to 0. This time I should probably factor. That should be my first step. So I'm going to factor x and x. And let's see, we've got a 1 and a 2. I need a negative there, so a negative and a plus. That should work. Once it's in factored form, it's easier to see what my vertical asymptotes, in this case, totes, will be. There are two of them. X equals the negative 1 from the first factor and the 2 from the second factor. Okay, so that's kind of nice. We have our first example where we have two vertical asymptotes. One's here at x equals negative 1, and the other is right here at x equals 2. So we'll see what that does to our graph. Our horizontal asymptote, that depends on our degrees. The degree of the numerator is less than the degree in the denominator, so y equals 0, because that's case number 1. So I will dash the x-axis, y equals 0. Let's talk about x-intercepts. The x-intercept comes from the numerator being set equal to 0, and that's not a difficult equation to solve. It's just 0. So I can plot 0, 0. And since that's the x-intercept, the origin, that means that the y-intercept should be the same thing. And you can confirm that if you cover up basically all of the terms, because x is going to be replaced with a 0, you'd be left with 0 divided by negative 2, and 0 divided by negative 2 is absolutely fine. That's equal to 0. So that's everything I'm going to do by hand. Now I'm going to pull up my calculator and see how I've done. I'm going to go to y equals, and I'll clear out that previous one. I'm going to put the numerator in parentheses, and I'm going to put the denominator in parentheses. Now I'm going to put the original denominator. I might have messed up my factors. There's a chance I messed that up. So I'm going to put the original in and make sure that it's in parentheses. So I have my x squared minus x minus 2. And I believe that's it. I'll push graph, and let's see if it fits into my shell. I've got that piece of the curve in the middle piece. Yeah, that fits nicely. I can see that there's like a little cubic type thing in the middle of my asymptotes. And let's see. So I've got this part right here.
You can't touch this.
And this is just a sketch of a curve. If you really need to get some exact dots, you could go to the table in the calculator, that's fine. Or you could just generate your own t-table by hand. Make sure you go through that intercept. And we're approaching the asymptotes, that's nice. And then let me see what the other part, and the other part does this curve up in here. So I will do that here. And that is a good looking function. Now that we see the picture of it, it's easier to possibly to talk about the domain and the range and the end behavior. So my domain, again, I know that the domain and the vertical asymptote values are basically synonymous. So x cannot be equal to those two values for my vertical asymptotes, -1 and 2. So that's the link between there. The range this time, let's talk about the range. If you're just looking at this part of the curve, the range is from -infinity to 0, but not including the 0. And if you're looking at this part of the curve, the range is from 0, not including the 0, all the way to +infinity. Well, who cares about these parts of the curves? I can use the middle part and realize that my range is everything from -infinity all the way through 0, all the way up to +infinity. My range is the set of all reals. Remember, the range is the greatest set that we have. So we do cross the horizontal asymptote right here in the middle. Okay, but the end behavior, if you have not already noticed, basically both ends will always be approaching the horizontal asymptote's value. So in this case, the far left end is approaching 0, the far right end is approaching 0 as well, and this is b of x is approaching 0. We could talk about asymptotic behavior, but I'm not going to do that on this one. We can see there's two different asymptotes. From the right of 2, the right side of 2, the function is going to infinity. The left side of 2, the function is approaching -infinity. The right side of -1, the function is approaching infinity. The left side of -1, the function is approaching -infinity. So we could describe those if we wanted to. Let's look at c of x. The first thing I'm noticing in c of x is that I might want to be factoring some of these things. I'm going to need to set the numerator and the denominator equal to 0, so it might make more sense for me to see them in factored form. I know I have a difference of 2 squares in the numerator, and I have a difference of 2 squares in the denominator. Yeah, so maybe I factor that. Okay, that might help me. So vertical asymptote, that comes from setting the denominator equal to 0. And now that I have it in factored form, I can see there's a -2 and there's a +2 that would make my denominator equal to 0. I'm going to use my plus or minus. Be fancy. And here's my x equals -2. Here's my x equals +2. Two vertical asymptotes again. Horizontal asymptote depends on the degrees. It might be easier from the original to see that the degree in the numerator is a 2 and the degree in the denominator is a 2. If it's in factored form, it's okay. It's still there. It's just hiding. There's an x squared and another x squared. In either case, you have the same exact degrees, which means that it's case 2, and we take our leading coefficient, which is y equals 2 over 1. So there's our horizontal asymptote. The intercepts are very helpful for helping us to make a pretty good sketch of our curve. X-intercepts, those come from the numerator being set equal to 0. Again, it's nice that they're in factored form. -3 would make the numerator equal to 0. +3 would also do that. So plus or minus 3 are my x-intercepts. So let's go to +3 and put a dot. Let's go to -3 and put a dot. The first time we've had 2 x-intercepts. And our y-intercept comes from setting x equal to 0. You could do that in this factored form, but there are a lot of places to plug in the 0 for x. I'm just going to go back to the original and plug in a 0 right in here and get rid of these two parts. Now understand what's left. We still have in the numerator 2 times -9, and in the denominator we have a -4. So that is -18 over -4, which would reduce to, I'll just say 4.5. I know that it's 9/2, but since I'm going to plot it, I might just say 4.5. I know I like improper fractions, but I need to know 1, 2, 3, 4.5, how to plot it on there. Okay, that's all I'm going to do by hand, and then I'm going to use my calculator to sort of double check that I've done that correctly. So I'm going to go back to the calc, and I'm going to put in parentheses the entire numerator, which is 2 and then x squared minus 9. There's 2 sets of parentheses there. The innermost, the inner ones around the x squared minus 9, and then the outer ones, which are telling the calculator where the numerator is, divided by another set of parentheses, x squared minus 4. I'm plugging the original equation into my calculator just in case I messed up my factors. So let's see, make sure that it fits into our shell, and here's our nice symmetric rational curve. Yep, I can see what's happening. So let's go over to here and put this part of the curve through that x-intercept, approaching our asymptotes. We have some sort of like a parabolic curve right here in the middle. I don't believe it's exactly a parabola though. And this part is going to go through that x-intercept. And there we go. We have enough of a picture to figure out what our domain and range is. Our domain, the same values that are the values of the vertical asymptotes, plus or minus 2. Those are my 2 restrictions for our domain. My range this time, range is very tricky. That's why I always like to see what the graph looks like. The lowest part of our range, we're definitely starting down here at -infinity, and then we get as high as this horizontal asymptote, which is 2. And both of these parts of the curves do the same thing. So we go from -infinity to 2, but we don't ever actually touch that 2. But then we skip a bunch of values between 2 and 4.5, and then we pick it back up right here at 4.5. So I'm going to union this with another interval. This time I get to include that starting point, that 4.5, and I can see that I'm traveling up the rest of the way to infinity. So range can get pretty complicated. I think it's best to look at the graph before we do that. Let's talk about end behavior. Both ends are doing identical things with rational functions. They're both trying to approach the value of this horizontal asymptote, which is the value of 2. This is c of x, and it will be approaching 2 on both ends. Our final example in this tutorial is d of x. I see that I might want to factor again, so this numerator I'm going to factor is the difference of 2 squares, x minus 1 and x plus 1. And divide that by x. Okay, so let's find our vertical asymptote. Vertical asymptote is x equals 0. Not very difficult to find that. Dash that in. Let's find our horizontal asymptote. Horizontal asymptote depends on the degrees. The degree of the numerator is 2. The degree of the denominator, is 1. This time the numerator's degree is bigger, so we do not have a horizontal asymptote. So that means that we might have a slant asymptote. And the slant asymptote occurs if the numerator's degree is exactly 1 greater, which it is. So we will have a slant asymptote, and we need to do that division. We could do long division, we could do synthetic division. This is actually not a very difficult one to do. I'm just going to do long division. X goes into x squared x times, because x times x is x squared, and that's actually it. We draw our line and we change our signs, and of course that cancels away. We're left with -1, and x doesn't go into -1, so we're actually finished. And we bring this right on over here, and we have our slant asymptote y equals x, or y equals x plus 0. Now, how do we graph this line? Well, like I just said, this is like x plus 0, so we started at the origin, and then we have a slope of 1. So up 1 and right 1, 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 up 1 and right 1. Down here, basically this diagonal line. I'm going to dash that in our first slant asymptote today. Let's find our x-intercept, if we have any. Set the numerator equal to 0. Yep, we have two different factors, so plus or minus 1 would be where we're crossing the x-axis, +1 and -1. And let's see if we have a y-intercept. Y-intercept happens when the x value is equal to 0. I might just do that from the original. If this is equal to 0, these two x parts, then I'll have a -1 divided by 0. Uh-oh, I can't have that. -1 divided by 0 does not exist, and it makes sense that there's something covering up the y-axis. Let's go to my calculator and see what we have this time. Clear that out. I'm going to put the original in, x squared minus 1, and divide that by x. Aha. Interesting this time, because our end behavior is going to be different. But this time the curve is still approaching the asymptotes, going through our x-intercepts. And it's kind of been, I don't know, stretched out a little bit because the asymptote is a slant asymptote. It's not too bad right there. So our domain is still everything except for the value of our one vertical asymptote, everything except for 0. Our range this time, let's see how low do we go. So we're definitely pointing all the way down. So -infinity is where we're starting. And then this part of the curve looks like it's going to continue forever. And if you don't think that it is going to continue forever here, then just take anywhere around here and go over to this part of the curve and let this part of the curve take over. This is definitely going to be pointing all the way up. We have a range of all reals again. This time our end behavior is different. Since we do not have a horizontal asymptote, our function is not going to be approaching a horizontal value, a line, a value. It's actually going to be increasing forever on the right end, and it's not doing the same thing on the left end, so I do have to describe as two separate statements. As x approaches positive infinity, d of x will be approaching positive infinity. That's the far right end. My function is going upward. But on the far left end, as x approaches negative infinity, d of x is approaching negative infinity. On the far left end, my function is pointing all the way down. So a little bit different when we don't have a horizontal asymptote. Thanks for watching this tutorial, and we've got one more tutorial about removable discontinuities next. I'll see you in class to practice this. Bring your calculators.